Hi guys, welcome to another Tenfold live show. It's really exciting to be here today. The show today is sponsored by Liberty. You can catch us on Monday to Thursday from 5 p.m. to 6 p.m. This week we're busy with 2D and 3D trig, and you can send in all your questions. However guys, next week we're going to be busy with a new topic. It's going to be factor and remainder theorem, or factorizing polynomials. All the videos that you're going to see today on the show are available on this really cool app which you can download from your app store on Android or iOS. There's a whole bunch of questions that you guys can still do. So if you want to test your knowledge, do a whole bunch of questions before you write a cycle test or before you go into your exams. Guys, get this app. It really is helpful for you. Guys, there is prizes that can be won. So have a look at our WhatsApp and our Facebook pages. You can stand a chance to win a TV, 19-inch TV, really awesome. Just send in all your questions for next week. It's going to be on factor and remainder theorem. So guys, we're going to go now to an intro video, and then we're going to be back in studio to answer a learner's question.
Trigonometry is used extensively in many different fields. It is a branch of mathematics that is not only useful, but fascinating too. Trigonometry improves critical thinking, geometrical reasoning, and problem-solving abilities. In the 2D and 3D trigonometry module, we take you back to the basics with revision of similar triangles and ratios, trigonometric ratios, special angles, solving triangles, finding angles, defining trig ratios on the Cartesian plane, the cast diagram, reduction formulae, trigonometric identities, and general solution. To be successful at 3D trigonometry problem solving, you will need to understand the concepts of solving triangles using 2D trigonometry principles and solving triangles using 3D trigonometry principles. Trigonometry is roughly 40 plus minus 3 marks in the final exam, which is approximately 27% of Maths Paper 2.
Hi guys, we're back now. Thanks for watching that video. We have a learner question that we're going to look from Anakin, I think it is, or Annika. Let's have a look at what she has to say.
Hey Tenfold, I'm Anika, and I just have this one question. It says in the diagram below, a circle with center O passes through A, B, and C. BC is equal to AC, which is equal to 15 units. BO and OC are joined. OB is equal to 10 units, and BOC is equal to X. And this is the question. Thanks, guys.
Okay, thanks for the question, Annika. Sorry about the mix-up with your name. I've been watching too much Star Wars. Guys, let's have a look at what the question has to say. It says here, in the figure below, a circle with center O passes through A, B, and C. BC is equal to AC, which is equal to 15 units. BO and OC are joined. OB equals 10 units, and angle BOC equals X. Okay guys, so I just want to read through this question once more, highlighting all the important bits, and it's quite useful to do this when you do a test or an exam, especially when it comes to Euclidean or trigonometry. Okay, so let's have a look at the question again. So it says, in the figure below, a circle with center O passes through ABC. Okay, so O is very important, guys, because what that means is it gives us a whole bunch of information regarding radii or lines in the circle. So we can say straight away that OB and OC are equal. OB is given to us as 10, so therefore OC is also going to be given to us as 10. Also guys, remember the angle at the center of the circle is equal to twice the angle on the circumference. So we can say then that this is going to be equal to a half x. Let's carry on with what the question has to say. It says BC equals AC, which is equal to 15 units. Okay, so let's look at our diagram over here. It says BC is equal to AC, and that's 15 units. So that means that ABC is an isosceles triangle. So that means automatically angle B can also be said to be equal to a half x. Lastly, it says BO and OC are joined. OB is 10 units, and BOC equals X. Okay, let's have a look at the first part of this question. It says calculate the size of x. Okay guys, so looking straight away into this triangle over here, x is located in triangle BOC. So we can say in triangle BOC, we do have two sides and, well, three sides actually, and an angle. Okay guys, so when it comes to this, when we have three sides and an angle, we're most likely going to use the cosine rule. And that's useful for us because we have all this information given to us. So using the cosine rule, whoops, my spelling has gone over there. Cosine rule. So in triangle BOC, using the cosine rule, we can say that BC squared is equal to OC squared plus OB squared minus 2 multiplied by the product of those two sides multiplied by cos of x. Okay, so substituting what we know BC is equal to 15. We get 15 squared is equal to 10 squared plus another 10 squared minus, well, 2 times 10 squared is going to be 100 and multiplied by cos of x, which is what we're looking for. So if we just do some manipulation over here, we're going to get 15 squared minus 10 squared minus another 10 squared, which is equal to minus 200 cos of x. Okay guys, so let's have a look at what this is going to be. I'm going to get 15 squared minus 10 squared minus another 10 squared. Whoops, another 10 squared. So we have 25 on this side, and that's going to be equal to negative 200 cos of x. If you want to solve for x, we're going to divide both sides by negative 200. So we're going to have cos of x is equal to 25 divided by negative 200. So guys, if you want to solve for x, we're going to use arc cos, which I'm going to write as cos, well, the reciprocal, well, the inverse function of cos, arc cos, which is going to be 25 over negative 200. So using my calculator for this, I'm going to have arc cos is 25 over negative 200. And that's going to give me a value of x is equal to 97,18 degrees. Okay, great. 97,18 degrees. Guys, let's have a look at the next part of this question. So it says calculate the size of ACB. Okay guys, so ACB is going to be this angle over here. We already know that this is equal to a half x, and this is also equal to a half of x. Right guys, so we can say straight away that this angle over here is going to be equal to 180 degrees minus x. But that's not what we're looking for. We're looking for the value of ACB, and we already know that x is equal to 97,18. So 180 degrees minus, let me just make sure that that is correct. It is 97,18, yes, correct. 97,18 degrees. That there is going to give me 180 degrees minus 97,18, and that's equal to 82,82 degrees. Okay, nice and easy one over there. The last part of this question, let's have a look at one more time. The last part of this question, and it doesn't seem to have come up over here. Guys, give me one sec. Oh, okay, well that seems to be the last part of this question then. Okay guys, so when it comes to something like this, we're normally going to look at one question that builds on to another. So in a test or exam, we don't want to make mistakes from going from one question to the next question. You do, however, need to realize of which sign rule or cos rule you have to use. This is based on the information given in the triangle. So guys, try not to make mistakes from one question going to the next, and read your questions very carefully, and hopefully this will help you going through to the next question. Guys, we're quickly going to go into a concept video, and then we're going to be back in studio with Philippa.
Since ancient times, mankind turned their heads skyward and found meaning in observed cosmic events. Interested in the position of heavenly bodies and the movement of the galaxy, one of the first sciences, astronomy, was developed. Mathematics was the fundamental tool that made exploring planetary motion and astronomical interpretation a reality. And some of the greatest breakthroughs in mathematics were made during the study of the stars. The origins of trigonometry can be traced back to the study of astronomy. The two main branches of trigonometry are plane trigonometry and spherical trigonometry. Plane trigonometry studies the relationship between the sides and angles of a triangle where the vertices are located on a flat plane. This is the type of trigonometry you're introduced to at school. Spherical trigonometry deals with curved triangles drawn on the surface of a sphere. This branch of trigonometry, which is used extensively in astronomy and navigation, enables astronomers to project the spherical heavens onto a flat surface for mapping. The positioning of heavenly bodies has always been at the core of astronomy. How do astronomers measure these heavenly distances which lie beyond the reach of measuring instruments? One of the most accurate methods used is called parallax. To understand what parallax is, try this. Place the index finger of your hand in front of your nose. It doesn't matter which hand. First, close your left eye and look at your finger with your right eye. Then close the right eye and look at your finger with your left eye open. What do you notice? Your finger appears to change position compared to the objects in the background. This effect is called parallax. Parallax describes the apparent change in position of an object against a fixed background due to the angle which the object is viewed from. In astronomy, this effect is called trigonometric parallax. The apparent movement of your finger in front of your face has a simple explanation. Your eyes are in different positions on either side of your face, hence they have different lines of sight to your finger. The difference in the angles due to the line of sight is the parallax, and the distance between your eyes is the baseline. The size of the parallax angle is proportional to the length of the baseline. By using parallax, the distance of the baseline, and trigonometry, astronomers can measure the distances to some stars and other objects in our galaxy without leaving the solar system. Stars are astronomically far away from the Earth. As the distance to a star increases, the parallax decreases. Astronomers know that if the parallax angle is too small to measure because the object is too far away, they have to increase the distance between the vantage points of the baseline. Since a star is so far away, its parallax is so small that using a short baseline, like the distance from one eye to another, will never work. We need a massive baseline to measure from. We have just that in the diameter of the orbit of the Earth. The distance from the Earth to the Sun, the closest star to Earth, is 1 astronomical unit, or AU, which is roughly 150 million kilometers. Hence, the diameter of the orbit of the Earth is 2 AU, or approximately 300 million kilometers. This is the baseline used to measure the distance to a star. The method of trigonometric parallaxes used to calculate the distance to nearby stars involves observing how the position of a nearby star seems to change as the Earth is in different positions in its orbit around the Sun. The line of sight to an observed star in December is different from the line of sight in June, when the Earth is on the other side of its orbit. The positions of the observed star, Earth, and the Sun make up the vertices of a triangle. Using trigonometry, the triangle is solved to determine the distance to the star. The angular shift, parallax, is one angle of a triangle, and the distance between the two vantage points, the baseline, is one side of the triangle. Since we have the length of the baseline, 2 AU, and can measure the parallax of the star, we can calculate the distance to the star. The majority of stars appear to maintain the same relative position for long periods. In fact, constellations identified by our ancestors are still seen today. So the observed star that we wish to know the distance to will not change its position significantly in the 6 months it is under observation. The closest star to our solar system is called Proxima Centauri, and it's about 4.25 light years or 40.2 trillion kilometres away. The Scottish astronomer Robert Innes, who at that time was the director of the Union Observatory in Johannesburg, South Africa, discovered it in 1915. Whilst interstellar travel at this stage may seem like science fiction, one thing is certain. If travelling to the stars were to someday become science fact, mathematics would be fundamental in achieving that reality.